This is Seung, and I'm the Principal and Director of Sky Academy, and in this episode, I just want to wrap things up. I want to congratulate you for coming this far and getting through all the episodes on exponential and logarithmic functions, and now it's the time to really wrap things up and just kind of bring a closure to this topic, right? And so basically we started off looking at exponential curves, right? Exponential curves being of the form f of x is equal to a of x, or in other words, y is equal to a of x, right? So we kind of looked at that, and we worked out that the derivative of an exponential function gives us another exponential function proportional to the first. So in other words, when we find the derivative of an exponential function, it gives us the same function, the original function, times a constant k, right? Which led us into thinking there must be a function that allows us to differentiate it, and it ends up being itself. Yes? So in other words, a proportionality constant of 1, right? And then in one of the episodes, we worked out that there is a special number for a, for the base, that will give us the derivative equaling the function itself, and that is the base being a special number called e, 2.71828, etc., etc., etc. It's a transcendental number like the number pi, which kind of goes on forever, doesn't stop. It's a decimal that keeps on going forever. It doesn't stop, it doesn't repeat, it just keeps going forever. So, okay, so that number e is one such transcendental number. It keeps going forever. And we've given, and the reason why we call it e is because it was discovered by Leonhard Euler, the famous Swiss mathematician, and we named it after him, and we called it the base e. Alright? And once we worked that out, all of a sudden, differentiating and integrating exponential functions became possible at a level that it wasn't before. Okay? And so we looked at the formulas for differentiating exponential functions. We worked out that the differential of e to the x is e to the x. We worked out that the differential of e to the f of x using the function of a function rule or the chain rule was f dash of x times e to the f of x. We worked out that integrating was just the reverse, all right? So we worked out that integrating e to the x dx will give you e to the x. That integrating an exponential function to a binomial function, so e to the ax plus b, will give you e to the ax plus b times 1 on differential of the power, which is 1 on a, alright? So it's 1 on a times e to that binomial, e to the ax plus b, alright? And because it's an indefinite integral, we've got to remember to plus the c, right? Once we worked out exponential functions, we were able to manipulate exponential functions so that it looked like a log function, right? And once we worked out the log function, we were able to differentiate log functions, and we worked out that the differential of a log function is 1 on x. So the differential of log e to the x is 1 on x, and then the differential of log e to a function is actually the differential of that function over that function itself, right? And then we're able to work out after that how to integrate those functions so that the result is a log, okay? So that basically just summarizes how we marry the whole world of calculus to the whole world of indices or exponentials and logs. We marry them together and we get this unit of work. So if you've been following up until now, congratulations on making it this far. I hope along the way that you've been practicing questions, alright? And if you haven't, go away and practice some questions on this. Get really familiar with it, because I look forward to seeing your success in 2-unit maths. And what I'm going to do right now is step aside to the side so that you can take in this summary. But I want to thank you for watching this episode and all the episodes in this topic. And I'll look forward to catching you on the next topic. Thank you very much for watching.